questions from last time? Break or anything else? All right, so again, there's no class on Friday. I will post another 20-point homework, which will probably involve using the Java wire building classes and some matrix interface class. Do some simple assignment, and I'll do another 5-point short answer question on Friday as usual. The 20 points due in a week, and the 5 points due on Monday, same as before. I wanted to mention again that I'm giving you an option of doing presentations in here if you want, for up to an extra 40 points for the semester. You can do it on pretty much anything. If you have an idea, shoot me an email, let me know. If you don't know what to talk about, but you have something that you're interested in, fault tolerance, self-organization, whatever, just let me know, and I'll try to bounce some ideas to you. Maybe we can figure out something that's appealing. And the same thing with class projects. If you have a general idea what area you're interested in, but don't know specifically what to do, just let me know, and we'll figure out something. Okay, and that's a really good way to pick up some points here. I wanted to do this on Monday, but didn't have the display working. But I want to just go over a little bit on wire building, a couple of examples. Before break came in, I had tried showing you some examples of the wire building class, and they weren't working very well. But that's because I forgot to compile them. So I'm going to try that again. So on the homework, to build a wire that starts at the top of the grid, moves down to the south, makes a turn, goes over to the east. Basically, there were 2 steps. You had to do an initialization step to create the original 2-channel wire, and then you use that to build the extension steps. The initialization step is a little bit different. But basically, using the memory version of the set and compile commands, the way to do this homework, control channel on the right, that makes it easier to take this turn at the bottom. You can do it the other direction, but then you had to come up with your own corner sequence. If you did it like this, you could just invert the one that we went over in class. So we put the PC on the left and the CC on the right, and since you're turning in this direction, you can start in the upper left corner. And making the initial head cells, basically you just turn on the control input on the first cell. So put this cell into C mode. And you didn't have to do this, but the pure way to do this is to configure this initial program channel and use that to configure the control channel. So you sort of take your data and route it into your control channel, put one into your control channel cell to make that a C mode cell, and that's all you're doing here. You compile those truth table equations into memory, and you say pump that into cell 00's data north. And now you have access to the cell's C input and the cell's D input while it's in C mode. And then you compile a new truth table, which corresponds to your initial control channel. Put this cell back into D mode so that it can actually configure the control channel cell, and then send that in again through 00's data north. But this time it's actually entering the control channel and configuring it, and then go back and configure the actual program channel. So set its control input to 1, put in the truth table for the initial PC, and pump it in, and that builds the initial cells in the wire. You can do this by just setting the control input on CC and feeding that in directly, but the sort of official way to do it is to only use the program channel. And then the extension step is almost exactly the same, except we're no longer controlling the C inputs of these directly, we're controlling them with the control channel. So instead of putting the control channel, instead of putting the C input to 1, we turn on the D input of the control channel, and then it's exactly the same equations. There's an empty matrix, and if we do the init sequence, it basically configures those 2 upper cells. Program channel is on the left, so that gives you access to the D input for the target cell, which is right here. And the C input is controlled by the control channel's D input. And now if we do this north-south sequence, it does what you would hope. Okay, we just continually use these 2 channels to build extensions to the wire. And one thing I just wanted to sort of illustrate here, if you were to break this wire, so we don't have a break line here, but if we were to clear out, say, cell 200, okay, that breaks the wire at that point. And now the target cell is down here, where we cleared out a piece of the program channel, and we can control its C input and its D input. If you don't have a pre-clear step in your extension sequence, though, so we can go ahead and we can build another piece of wire, reconfigure these 2 cells. But as soon as we do that, we've actually extended the wire further than we expected. We've got control now all the way down here at the target cell. Okay, if you take 2 pieces of broken wire and just join them, then you get a whole piece of wire out of it. So the pre-clear step is basically just removing wire ahead of where you're building. You didn't have to do that for the assignment, but if you don't do that, you can't run that sequence twice because your wire is facing the wrong direction. Okay, the other thing I wanted to show you was those Java examples from last class before the break. So this was a class called Test2. It basically creates a cell matrix interface object, okay, which will output to test2.sequence. It creates a wire building object using the cell matrix interface. It says the wire is going to move to the south. The rightmost, the most counterclockwise corner of the wire, moving in this direction, is right here. So we tell it 0, 1, and that'll put the wire all the way over to the left. And in this case, the order of the wires, CCPC, I think it's like that, actually. And we are putting on a pre-clear flag, so it'll clear out in front of it. And then your whole homework assignment is basically this simple set of calls. Initialize the wire that builds the initial head cells, extend it in the current direction, which is initially south, 10 steps, make a counterclockwise turn, extend it 10 steps, and then close the sequence file that we're writing. Creates a sequence file, which we looked at last time, although it was the wrong one because it wasn't compiled. But if we run that, turn the update rate down to 128, so it only updates after every programming cycle. as what you want it to do. Goes south, makes a counterclockwise turn, and runs back to the east. And in this case, we can clear out a cell in the program channel to break the wire. And if we rerun the sequence, it'll actually do the correct thing because it's got a pre-clear step. So you can sort of see it's wiping out the cell in front of it before it builds, so it doesn't automatically join up to a new wire.
It seems like it's building a lot faster to the south than to the west. Is there?
Yeah, there's more events taking place the bigger the wire is. It's just a phenomenon of the simulation. When you want to send a signal to this cell down here, it has to trickle through all the way.
Oh, so it's just an overall slowdown. There's not more steps.
No, there's not more steps. It's just the simulator has to do more work.
Yeah. Okay.
Did you get it open? It took me 10 minutes. I don't remember if I had to Google it or not. And then just to give you an idea, this is another example, test 3. Again, standard cell matrix interface. Start an initial wire, and this is just going from west to east. Turn on the pre-clear. Initialize the wire and extend it one step. And then, this is just for fun, we go into a loop where we basically extend the wire 10 steps in its current direction, make a clockwise turn, make another clockwise turn, so that's a U-turn. Extend it out 10 steps, make 2 counterclockwise turns, and we do that inside the loop. So it does it a total of 4 times. Okay, there's a sequence file. These can get pretty long, so that's 1,300 lines. 4 channels, so, sorry, 3 channels. So 1,300 over 3, it's about 430 programming cycles to do this. Each one's 128 bits. And if you run this sequence file, it just sort of moves across, makes a U-turn, comes back the other way. And we'll keep doing that for a total of 4 pairs of rows. And you can see pretty clearly here the slowdown that you were talking about. If you actually looked at the number of time steps, it's moving at a uniform speed with respect to that. E is showing you the number of events taking place. I don't know why it's not updating more quickly. I think it only updates every 100,000 events, 100,000 time steps. But the number of events is growing linearly. The rate of increase is linear with respect to time. And that's the big problem with the simulation on a standard machine. The more interesting your circuit is, the more parallel it is, the worse the simulation speed. Ideally, you want a system where there's millions of things happening all at the same time, and those are the worst ones to try to do a simulation on. So that's a problem. There's been some work on parallel simulation over multiple CPUs. That works well sometimes, not so well other times. Some good project ideas there, though. So I think I posted the Java files for test 2 and test 3 under the resources tab, and like I say, with Java, it's useful sometimes to just kind of take an example file and then just modify it to do whatever you want. So that can be a sort of quick path to getting this stuff working. Okay, any questions? questions so far on that?
I noticed you were able to turn the wire the other way too.
Mm-hmm.
Last example. I was wondering if that was possible.
Yeah, definitely.
Looks more complicated to
Yeah, like I say, depending on where you put the PC and CC, it can be easy or hard to make the turn. If your PC is over here and your target cell is always in front of the program channel, so when you have access to this, it's a little harder to build these cells over here. If your program channel is here, it's a little easier, but it's a pretty small difference. It's worse when you have a break line thrown in there also. And the wire building class does not extend break lines around corners, just because I didn't write it. Okay, so what I wanted to talk to you about next, the loader program, which you used for one of your homework assignments. It's good for some things, it's not good for other things. The benefits of the loader program, it's really good for wiring. Once you get sort of proficient at the keyboard shortcuts and you're used to taking pieces of wire, putting them down, rotating them, doing the ore pasting so you can put them on top of other cells, wiring can be really, really quick. Okay, so when you've got a bunch of subsystems, you want to put them together or move them around, it's actually a fairly efficient tool for that. It's good for circuit reuse. You can have some circuit you build, a multiplying block, something like that, and when you want to take that and pick it up and put it somewhere else, rotate it, whatever, that's all really fast. And because it's graphical, it's easy to visualize. So if you have a layout on a piece of paper for how you want to construct your circuit, it's fairly straightforward to go from that to an actual layout using the loader program. But it has some disadvantages, one of them being every time you want to create a new cell, you have to open the cell editor window, and you have to go in and type in these equations and compile them by saving it and so on. And that's doable, but I don't like pointing and clicking personally. I'm much faster on a keyboard. And it really forces you to sort of interact graphically. And if you had a bunch of equations that you output from a Perl program, say, and you wanted to compile those into a set of cells, you can't really do that with the loader program. The icon editor is also a weak spot. It will let you create icons, but it's not ideal. It takes time, especially if you want to put labels on your cells or label inputs and outputs. It's a fairly cumbersome way to go about creating those. And the libraries and grids that you create with it just don't really port very easily. If you wanted to take a whole bunch of cells that you've created and move them to another machine, or archive them somehow, or send them in an email to someone, it doesn't really work very well. It's sort of tightly bound into the loader program itself. You need to run the loader to sort of see what's inside these libraries and grids that you've created. So there's another tool that's just called the library compiler. And like a compiler, it basically inputs a plain text file in which you specify one or more cells that you wish to use. And you feed this file into the compiler, and it basically produces a .lib file, which can be read by the loader. So it's a way to create the bare cells. You can do a little bit of layout in terms of putting cells next to each other, but it's not really ideal for building a large-scale system. It's really for building the basic cells themselves, which you then use in the loader, and you drag and drop and move around and so on. It also outputs a grid file, which you can use as basically a palette. It just gives you a place to copy in each of your cells from to paste elsewhere, so you don't have to actually load them from the library. The graphics are a lot easier, and it's also smarter about color. The loader handles 32-bit color, whereas the icon editor handles 3-bit color. So that can be useful. So I'm going to upload the pieces for this into the resources area this morning. You run it similar to how you run the loader, java-class path. You'll specify the libcomp.jar file, which you can download, and then the famous -d libroot argument, which is some directory pointing to your library area, followed by a slash. Okay, and the slash is critical. And then libcomp is the name of the compiler itself, and then you feed it the name of an input file. It has pretty minimal error checking. If something's wrong, it'll tell you something's wrong. I think it'll spit out a piece of the input file that it choked on, but it's not really good with diagnostics, so it's best not to make mistakes. And there's another file, colors.txt, which you need to have in your current directory, and I'll post a sample one of those. And again, it takes in an input file and outputs two things, a .library and a .grid. The library file is also stored into this libroot directory, so as soon as you compile your file, the library is automatically accessible. It's automatically available in the loader, but it also puts them in your current working directory. The input file is a pretty simple format. You can have comments with a semicolon, blank lines are ignored, spaces are generally ignored. You basically begin your file with a start statement, so you say start and the name of whatever you want the library to be called. You put in all your cell definitions, then you say .finish. And everything in between there gets compiled into this library. And you can have multiple start-finish blocks. And I'll show you an example in a minute. General commands, you can say .bg and put in a color. So all the colors, I think they can be 6-digit hex numbers, which will be an RGB value. Or you can use a name from this colors.txt file. And colors.txt just pairs 6-digit hex values with names. So you can say blue, green, navy blue, sky blue. Background color says what the background color for each cell should be. You can say color1 - color2, and it'll sort of gradiate the collection of cells. The upper left corner will be the first color, the lower right corner will be the second color, and it'll move them in between. That's questionably useful, but it could be nice if you're making a bunch of cells which are going to be used collectively as a single unit. It's a nice way to sort of delineate a region of the circuit in the loader program. You can say .border and a color, and it'll put a border around the whole collection of cells. You can say .text color, and it'll tell you what color the text should be. And you can say .size, height, comma, width. You have to specify a size, and that says how many cells you're going to define within this block. You don't have to define all of them, but it will define them. They'll be empty if you don't specify those cells. And then when you want to actually define a cell, it begins with a .cell command. You can say either .cell, and it will use the next cell, so it'll begin in the upper left corner, move across, and then come down, so it's a row major ordering. You can say .cell, or you can say .cell and specify a row column for the cell you're defining. And once you do this, if you say .cell, it'll be the next cell after that. So it basically just sweeps row major order through this collection of cells. Let's see, .text will display a small string inside the icon itself, and you can be up to 5 characters on 3 rows, so a total of 15 characters. Not the prettiest font ever, it's a 5x3 font, but it works. And if you use an underscore, it'll insert a space. It knows about some punctuation and stuff like that, but if you do an underscore, it'll put a space in. And spaces are actually really useful. A lot of what you can do with the cells you define here is just use them as decals. So you can have a cell that has an empty truth table inside, but has an interesting icon. And if you take that and or paste it on top of something else, you can just put some text on top of another cell, or you can label some inputs and outputs. Or you can add a border, or a color to the background, things like that. So there's different ways to use this tool. And in the cell body itself, you basically write Boolean equations for your truth table. Again, reverse Polish notation. You can have comments, and then you can have these I/O statements that label inputs and outputs. Basically say .io space, and then something like DNI for data north input, or CSO for control south output. And that tells it where to put a label, and then you can put a label itself, again, up to 5 characters, but these icons are 32 by 32, so you don't have a lot of space. But it'll put a label in the cell at that point, and it'll be aligned with sort of the standard input-output locations that you see in the icon editor. So if you stick with that convention for where you go in and out of each cell, things line up nicely. And when you take a wire and point it into a cell, it'll line up with any of the input labels on that side. And then you can also specify truth tables in terms of the actual bit values that you want. So you can say .bin and put in a series of 1s and 0s. The better way to do it is to say .hex and put in a series of hex characters. And you probably want to use .h3x instead of .hex. That's a kind of technical detail. The truth table format changed in the current version of the tools. It's this sort of more general, extensible format. But the loader still outputs the old style version 2 truth tables. So when you feed a binary file into the simulator, it automatically updates the truth tables from version 2 to version 3. If you're specifying a particular bit pattern, you don't want that translation to happen. You want to actually specify the bits in the exact order you want. So if you say .h3x, it'll put a tag in the file which tells the simulator not to rearrange the bits. And you can actually say ... in these things. So if you say .hex 0, 0, ... 0, F, and it'll fill those in with zeros. So you don't have to actually write out 32 characters. Although it's not too painful. It's more of the binary. That's not terribly sophisticated, but the obvious cases where you want to extend zeros, it seems to work. And then there's these mysterious descriptions. You can say .desc, and it will let you put in multiple lines of text up to 1,024 characters that get embedded inside the binary file for that cell, and you end it with a .end statement. And those actually are available in the simulator. I think I mentioned before that I didn't think they were supported, but they actually are. When you point on a cell and you see the truth table for it, you'll also see the description between angled brackets. So it's just a way to sort of pass a little bit of information between the loader and the simulator. So as an example, this doesn't really do anything useful. It's just purely an example. Plain flat file, semicolons for comments, a start statement, and then I'm creating a library called Nick Test. Again, keep everything uppercase. I don't think it matters, but it's safer. Specifying a background from red to white, and colors.txt. I just ripped off the web somewhere. But basically, any of these colors, you can specify in a statement that needs a color, or you can use your own file. If you want light steel blue too, you can do it. Navy blue border, text is black, and then I'm specifying a 4x4 set of cells. So this is going to create a library containing 16 cell definitions. And I say .cell, I'm not telling it which cell I'm after, so it's going to define this cell here. It's going to put a label control in there. This is the crystal controller. These are the equations. And then the data west input, I'm going to label X. That's actually where your crystal would go. And the data east input, I'm going to label go. And this is like a cell that you defined for another homework problem. You take the eastern input and you use that to drive the western control output. So that puts the crystal into C mode. The western output recirculates the crystal values, and it also gets copied over to the east. Okay, that's just an example of a crystal controller. And then you define another cell, which is a 3-input AND gate. And you write the Boolean equations for it, and you label the 3 inputs, A, B, and C, on the 3 different sides, and the output X, and so on and so forth.
So when you don't define which cell you're going, it just goes to the right.
Yeah, it basically goes to the next one. So
Yeah.
you do it 17th cell, I think everything blows up. These are labels again. I just define a cell and I put a text value in the icon, but I don't define any truth tables. There's another cell called clock. You can or paste them in the loader, and all they do is add text to the icon, which is useful. So like I say, they're kind of like decals. Binary definition of a cell. So this was a crystal, 11110011, and everything else is 0. And then another crystal with 32 pairs of 0, 1s, and whatever you want, and then a finish statement. libroot does not like things like dot or twiddle or symbols or things like that. It has to be a fully specified path. But again, specify the class path wherever you put libcomp.jar. Libroot exactly the same as you did for the loader program. Ended with a slash space. Libcomp is the name of the compiler and then the name of the input file. It'll tell you each library that's compiling and when it's done, and that'll leave you with nictest.lib and nictest.grid. And like I said, the lib is also copied into the main library that you specified. And the grid file is a palette. So if you open nictest.grid, you get these cells that you defined. So we defined 10 of them in this case. There's the original one, control. There's the X output on the west. There's the go input on the east. And if you edit this, it's just got the information that you defined in the flat file. And most of it just copies pretty directly. There's not a whole lot of translation that goes on from your input file to what ends up here. But it's an easier way to define these things instead of having to go through the cell editor window and so on. And it gives you a nice flat file that you can work with easily. You can make backups, all of that stuff. There's one caveat here. Once you define a grid like this, be really careful about making changes to it. Okay, it'll mess you up badly. You can change what's in a particular cell if you need to change an equation that you typed wrong or something like that. You can go ahead and do that. But once you start using these cells in other grids, don't change the ordering of these. Okay, because these things are labeled like cell 0, 0. Cell 2, 3. Okay, they're just given these positional labels. And if you go back into your input file and you make a change and define some other cell up here so that these things change their position, it's going to mess you up because this is cell 03. If you define some other cell in the beginning of your file and everything shifts over, this is going to be cell 03. And if you've already used this in grids, they're going to be pointing to the wrong cells. Okay, so just be careful once you do these. If you need to make new cells, make sure you put them afterwards in empty spots. Same thing with the size. Don't change it. You can make the number of rows larger, but don't make your grid wider. Because if you do that, then this would be cell 04 instead of cell 10. And again, anytime that you use this, it's going to be pointing to the wrong cells. Other than that, it's a pretty safe tool. So, and for me, it definitely saves a lot of time.
So you could avoid those issues by not editing this through the interface, only editing it in the lib file.
Well, even if you edit the file itself, if you change the dimensions or if you add cells that change the ordering of these, it's going to get you in trouble.
Right. Yeah. I mean, if you reference it on the design you're already using.
Right.
Yeah.
Right. And you can edit these with a loader, but that sort of defeats the point of having a flat file input. And if you change these with a loader and then you recompile your flat file, your loader changes will get undone. So you just need to be real clear what you're editing and where you're putting things. And if you take this library and you rename it and put it somewhere else, then you can just treat it like any other library. But it's totally good to keep them separate, the things you're doing with the loader and the things you're doing with the library compiler. And the other thing, so let's come back in here and let's change cell 0. Change that first cell's truth table, and we'll change its label to just output 1s on its D outputs. And recompile. Okay, so that's done. But in the loader program, so normally you'll be using this, you'll keep a loader program up, you'll be using these cells. We just tried to change this cell up here, but of course if you go and you look at it, the icon's exactly the same as it was. And if you look at the truth tables, they're exactly the same as they were, okay? The loader has a cache, so it doesn't have to keep pulling things from disk. So if you make changes to any of these libraries, and you already have your loader program open, you already have a grid open, you're using all this stuff, go to Edit and say Flush Cache, okay, or Control F. And when you do that, that'll reload all of the cells from all of the libraries. And now we see the correct icon there, and if you go and you look at the truth tables, you'll see the new Boolean equations. Okay, so if something's not happening, try flushing the cache. And you can always do that, and it doesn't do any harm. It just takes a little bit. So if you're in doubt, just do a Control F. Okay, so hopefully that will be useful to you if you start trying to make larger circuits. Way to define cells inside libraries. So I'll post the jar file, I'll post colors.txt, and I'll post that sample flat file on the resources page after class. All right, any questions? Okay, we'll end a little early today then. I'll post some homeworks on Friday, and like I say, let me know if you want to talk about presentations or projects, and Monday we'll get into something different. All right, well, have a good weekend then. That's part of a project started a few years ago called One Laptop per Child.
Oh, this is your one.
Yeah.
Why is there 3 touchpads?
Good question. These kind of seem to be pressure sensitive
Yeah.
to some degree. Originally they were supposed to be like a writing area that you could use a stencil on to write, and I'm not positive if there's anything under there or not, but I think I've used it with stylus, gotten it to work, which takes a lot of pressure.
Does this come with Linux on it, or did you add it yourself?
It comes with a system called Sugar, which is a really cool little operating system they made basically for kids. Very kind of intuitive interface. There's
It's a little lines over there.
there's a drawing program. I don't remember the name of it, but it basically lets you say, it's kind of like TurboGrafx was. It lets you say, here's my stylus, move to the right a certain number of spots, and now move downward. And then if you want to do that a bunch of times, you can put it inside a loop. And you can say, if you've reached the end, then change the color to this thing. And so you're a kid, you're playing with this, you're learning how to like make pictures and stuff, but you're actually learning how to program, how to create algorithms and stuff.
Sorry.
Change.
It wasn't user to user. Because I had hoped.
It's OLPC,
Like I've written some values.
OLPC, Mr. X to
Oh, did it tell the people they need to start XCS Windows?
No.